So this is lecture 6. Last time we learned about permanent, which is a useful tool to count the number of perfect matchings in bipartite graphs. But the shortcoming of the permanent is it's difficult to compute. On the other hand, determinant is easier to compute, but there is this downside that we have this sign part. So we write this sign of a permutation to be 1 or -1, depending on this is even permutation or odd permutation. Let's write it this way. Sometimes you write this as 0 and 1, but here let's write it simply as 1 or -1. So this part, this term, is useful to useful to count the perfect matchings as it is. But because of this sign part, some of them cancel each other. So it doesn't really count the number of perfect matchings. So one of the way that we can try to overcome is maybe we change this A. In there, this is bi-adjacency matrix or adjacency matrix in situation. And there we have like some 0 and 1. And we change some of the ones into -1. Then this term will have a different sign. If by chance, after changing this to 1 or -1, if this entire thing always becomes a non-negative number, then it can actually be used to count the number of perfect matchings. So that's what we will do today. So we will focus on adjacency matrix rather than bi-adjacency matrix. And let's define some concepts before we actually introducing what we will use. We say a square matrix A is skew-symmetric if transpose of A is same as its minus A. So for example, if we have some matrix, and if we want it to be skew-symmetric, then its diagonal must be all 0. Because if you have say 1 in the diagonal, then in its transpose, you again have 1 in diagonal, and then you take the negative, then these two cannot be same. So number x and minus x can be same only when it is 0. So skew-symmetric matrix must have a 0 on the diagonal, and then everything else must be symmetric in this sense. If you have some number, and its number at the aij is 1, then aji must be negative aij. So this matrix is skew-symmetric. And if we have an oriented graph, or more generally directed graph, let's just focus on oriented graph. If you have an oriented graph, let's say U1, U2, U3, you have this orientation of the edges. If this was an undirected graph, then we could have U1, U2, U3, U1, U2, U3. We could consider its adjacency matrix, which is simply this. For the oriented graph, what we can instead thinking is that if an edge is from U1 to U2, then we let A12 to be 1, but A21 to be negative 1. So 1, 2 is the correct direction, and 2, 1 is the opposite direction. So you can give this number. So this is negative 1. And 3, 2 is negative 1. And 3, 1 is negative 1. Then we can consider this oscillation matrix for oriented graph. And we know that this oscillation matrix for oriented graph is skew symmetric. From this definition, always Aij is negative Aj. If there is no edge between two vertices, then it's 0. So negative 0 is again 0, it's fine. And if there is an edge in one direction in oriented graph, then it gives you, it makes one of these two to be 1 and the other one is negative 1. And for an even number n, let's consider the graphs with n vertices. And now we want to talk about perfect matching. For that, it is necessary that the number of vertices n is even number. And permutation sigma of Sn. Now we want to correspond the matching with permutation. So in by oscillation matrix, it was natural. There are, natural way. But for oscillation matrix, it's not really that, obvious how we want to do it. Because in the oscillation matrix, if you consider a permutation, say 1, 2, 3, 2, 2, 3, 1, then vertex 1 to 2 to 3, and if you just connect the I and sigma I, then you get this triangle instead of perfect matching. So it's, not the same way as we deal with the bi-oscillation matrix. So we designate some way to, correspond the permutations with the perfect matching. Let M sigma be the perfect matching. Say sigma 2i minus 1, sigma 2i for all I from 1 to n over 2 over, say, complete graph. So we didn't really fix the graph G yet, so we don't know whether this matching is even in the graph G. So let's just consider, any case as a perfect, complete graph. Then this give you a matching. So for example, if you have sigma, which is 1, 2, 3, 4, 5, 6, and this is, say, 3, 5, 1, 2, 6, 4, 6, 4, yes. Then M sigma is simply you take 1, say 3 and 5, and 1 and 2, and 6 and 4. If you take, say, 1, 2, 3, 4, 5, 6, 4, 6, 1, 2, 5, 3. This different permutation this is 1, 2, 5, 3, 4, 6. So this 2 would give you the same matching, same perfect matching. So this is one of the natural way to, and one of the obvious way to correspond the perfect matching to, permutation to perfect matching. But one downside is that the two different permutation could give you the same matching. So with this correspondence, we want to give some weight to a matching. For a perfect matching, M, which happen to be corresponds to a permutation sigma, and this is a perfect matching in complete graph, and a skew symmetric matrix A, which has entries Aij. We want to define the weight of M B. Let's write weight of M as sine of sigma times A sub sigma 2i minus 1 sigma 2i. So what it means is that we have these edges. If you have some skew symmetric matrix A, then here we have some entry A35, A12, A64. And we multiply them, and then we multiply the sine of sigma. That's our definition. However, there is some problem. There could be some problem because this is M and this is M. We can either choose this sigma or sigma prime. Let's say the second one is sigma prime. If we choose sigma prime, then we have to multiply A12, A53, A46, and then multiply the sine of sigma prime. So we need to check that whether if we choose this sigma, then we get certain number as a weight. And if you choose sigma prime, we get certain number as a weight. We have to check whether this weight and this weight are same. But we already know that A is skew symmetric. So this number and this number differs by -1 up to, in the multiplication. And this differs by -1. So multiplication of these three numbers are actually same. And if you check, then this is actually 1, 2, even permutation. And this is also even permutation. This is even because you have to take the transposition and transposition, then you get the identity matrix. So this is even permutation, identity permutation, and this is even, and you can also check that this is even. So we can actually check that the choice of sigma doesn't really matter in that case. More generally, we can actually show that whatever choice of sigma we take, this will give you the same weight of M, so it is well defined. Because if two permutation sigma and sigma prime both corresponds to the same matching M, then we can obtain one from the other by series of the following operation. So, say switching sigma 2i1 to sigma 2i minus 1 and sigma 2i, or switching sigma 2i minus 1 and sigma 2i pair with sigma 2j minus 1 and sigma 2j for some ij. So what it means is that here, say this was 6 4, but now 4 6. You flip it. So these are flipped. So that's this first operation. And second operation is that here you have 3 5 1 2, but here 1 2 5 3. So what you do is you change this to 1 2 and 3 5. That's the second operation, and then you flip. That's the first operation. So it's obvious that if two permutations give you the same matching, then these two are matched. There are two important elements, whether 3 comes first or 5 comes first. And then once you fix that, the next one is in which block out of this n over 2 blocks would you put this in. So first decides which one comes first, and then second decides which of the block that you are gonna put that pair in. So that it's obvious that these operations actually changes sigma to sigma prime if they define the same matching. But it's easy to check that this operation does not change the value of this expression. Because once you switch these two, one term will have a different sign, but sign also changes, so it stays. And then once you change this, two pairs, then none of these terms changes and sign also will stay. So you can check that this is actually well defined. And now we define what's called Pfaffian. A is a skew symmetric matrix, let's say. Say n by n matrix with even number n. And we define Pfaffian of A as following. We just take the all matchings, all perfect matchings, and we add the weight together, where this M runs over all perfect matchings of the complete graph Kn, having the vertex set corresponding to the rows and columns of the skew symmetric matrix and A. So now we have defined what we wanted. So what we want to do is the following. We want to say that this Papian is useful for counting matchings, counting perfect matchings. But in order to do that, we need to show two things. It actually counts the perfect matching, and then it's easier to count, easier to compute than, say, permanent. So what we essentially want to do is that we want to show that for some graphs, we can orient the edges of the graph so that adjacency matrix of the orientation so that for adjacency matrix A of the orientation, this Papian actually counts the number of perfect matching. In other words, somehow the weight is miraculously all positive number, all non-negative number, so that it actually counts all the matchings which lies inside the graph G. And also we want to show that its Papian is easy to compute, sorry. So let's first show the second one. There is this theorem by Kelly saying that essentially computing Papian is as easy as computing determinant. If A is a skew-symmetric n by n matrix with even n, then determinant of A is Papian square. So instead of computing Papian, if you just forget the sign, plus sign and minus sign, it doesn't really matter as long as, in our purpose, the sign really doesn't matter as long as all the weights have the same sign. So as long as we don't care about the sign, then we know that if you compute the determinant, then we know the value of Papian. Yep. So we will prove this. To prove this, essentially how we want to prove this is, if you take a permutation, one of the natural ways to use this permutation to get a perfect matching in bipartite graph was that when we have I and this sigma I and sigma I. So in bipartite graph and bi-adjacency matrix, if you have a bijection between the parts, then you add an edge, then that gives you a permutation. But in adjacency matrix, we are no longer in bipartite regime. So if you do that, you actually get some cycles and edges. So it could be that J go to sigma J, while sigma sigma J is same as J. Could be there is one fixed element, K equals sigma K, or some other cycles. So sigma actually gives you this, and also with our definition, it also gives you some matching. And as proving one of the previous theorem in last time, we actually take a union of two matchings, and then that give you a certain graph, and we use that to deduce certain theorem. So we proved the upper bound of the perfect matching, number of perfect matchings in general graph with some given degree sequence. There the trick was that if we have a disjoint union of even cycles and edges, then that can be considered as a union of two matchings. So similarly, this graph, if there are no odd cycle part, then this part, no odd cycle or fixed points, then this can be obtained from a disjoint union of two perfect matchings. And we want to somehow use this here, because this Pfaffian is roughly summation of the matchings. We define this weight, but this is essentially summation of matching. Once you squared it, then these terms becomes multiplication of two matchings, M and M prime. And then we want to somehow connect that M and M prime with this permutation, where determinant is sum over all permutation. It sums up some terms over all permutation. So we want to make some connection between those two. For that, let's first consider the specific type of this permutation, which doesn't contain any fixed point and which doesn't contain any odd cycle. So let E sub n be the collection of all permutation, so that every cycle of sigma has even length. We define this cycle of the permutation. If we have this permutation, then that gives you 1, 2, 3. So we have cycle of length 3. And 4, 5. This is cycle of length 2 for this permutation. And 6 is a fixed point, so it's a cycle of length 1. So that's this cycle. This is not graph cycle, but the definition of cycle in permutation. Then what we want to show is then there exists a bijection T from En to say curly M by curly M, where let's say let curly M be the collection of all perfect matchings in complete graph. So this is what we want to prove. So we want to prove some correspondence between pair of perfect matching and some permutations. So proof of the lemma. So for each cycle in sigma, let I be the smallest index in the cycle. So if we have a sigma, which is a 1, 2, 3, 4, 5, 6, 7, 8, and let's say you have 2, 3, 4, 1, 7, 8, 6, 5, then you have 1, 2, 3, 4. This is one cycle of the permutation. Let's see. And in each cycle, you choose the smallest index. And assign the edges I, sigma I to m, and sigma I, sigma I to m prime, and so on. So meaning that this edge goes to m, and this edge goes to m prime, and this goes to m, this goes to m prime. And of course, for this, permutation cycle of length 2, which corresponds to an edge in the graph, we add these two, both matching. Then blue matching is m, green matching is m prime. We let t of sigma be m, m prime, as all cycles, this permutation cycle, have even length. This is a well-defined map. So we want to show that this is actually bijection. So conversely, if we have some m, m prime in this curly m by curly m, what we do? We simply take the union of 2. So we have this m and m prime, then we take the union of 2. Then you get 1, 2, 3, 4, and 5, 6, 7, 8. And so let's draw it this way. And we orient each cycle such that the lowest index I in the cycle, we have I, sigma I is in m. So here we have two ways. So we either direct this so that the 1, 2, 3, 4 maps to 2, 3, 4, 1 in the permutation, or the other way around so that the 1, 2, 3, 4 maps to 4, 1, 2, 3. But out of these two choices, we make that from lowest one to, its image comes from the edges of the first matching. Then this will give a permutation sigma such that T sigma is m comma m prime. So this shows that this operation is inverse. It gives the inverse mapping of this T. So T is a bijection. So this proves the lemma. Now using this lemma, we are ready to prove this theorem of Kelly that the determinant is actually Papian square. So that's what we will prove in the next video.